temporal logic counts. To enter in negative pi and the operation subtract, 10 steps to enter 9 actions. 90% efficient, 10% of the cost is overhead. To perform the final test from the beginning, from the spec, 30 steps for 18 actions, or 60% efficient, 40% cost is overhead. The spatial counts. Again, negative pi up to the subtract operator. 54 steps for 9 actions. 16.6% efficient, 83.3% of that cost is overhead. To perform the final test, 96 steps for 18 actions. 18.75% efficient, 81.25% cost overhead that you have to maintain. Look at at the logic trace associated with entering in just the negate on the first operand. 27 logical tests were made. The temporal state diagram. This is a simple state view. Each state does one thing well. That is, each state makes a true or false decision and transitions to a true or false destination. Nothing more, nothing less. This is a good example of keep it simple. Compare temporal to spatial. Look at the number of arrows coming into op entered. I'm not sure that you can see this, but when you download the presentation, you'll be able to see that there's a negated 1 here, a negated 2 here, an operand 1 here, an operand 2 here, a fraction 1 here, a fraction 1, I made a mistake. A fraction 2 here, and a fraction 1 here, an int 1 here, and an int 2 here, and a 0, 2 here, and a 0, 1 here. He had to duplicate his routines to keep the values separate. Sorry about that. On the temporal side, I have a single negate that I use in my both operand 1 and operand 2. I have a single digit value that I use for the integer portion and the fractional portion because I'm just building a number, and I combine that with a decimal point, and it could be a number that includes exponents and everything else if I chose to design it to that point, but this was not my specification originally. It came from the author. The other author, I should say. The difference is that I can explain this state diagram to someone that doesn't understand computers. This one I can't explain to someone that does understand computers. On the temporal side, you can see that this is the first operand. It's boxed in here, says oper 1. And I can show you the number, negate, digit, decimal point, digit, clear entry, clear. I would have to explain a little bit about what this push means to somebody, but I believe they can understand that I have to say values, and that's what that push is doing. Likewise, for the operations, add, subtract, multiply, divide. It's that simple. The second operand, I have an I off here, and I have a save down here. I'd have to explain those two. But the similarities between the two are these two pieces have identical pieces of code. And the result, percent equals chain and error. I think that a non-computer person could understand why those are there. Again, I can't explain this spatial, standard, traditional state chart to a person that even understands computer science. If you look at the complexity, to me, this was one of those things that kind of stood out. I tried really hard to move these procedures around so that it would simplify this diagram when I was doing this in Visio. No matter what I tried, I could not simplify it. Summary. Thought we'd never get here. I hope this presentation encourages you to take the challenge and see for yourself. If you look at the efficiencies between temporal entering in negative pi and spatial entering in negative pi, again, it is like night and day. The overhead is way down. That means that your cost, your complexity is also way down. If you look at the actual calculation of the final test, those 18 actions that have to be taken. The temporal approach is 60% efficient with 40% overhead, compared to the 18% efficiency and 81% overhead. Does not look well for the spatial folks, and that's what most software is right now. Why is time important? Imagine the complexity of hardware logic without a program counter. That complexity exists in traditional software because it does not have a time index. Understanding time in software means not having to do an if to test where the program is executing and what happened. It took me 23 logic points to implement the temporal calculator example. It took 112 logic points to implement the spatial calculator example. When you look at this slide, you ask, why are there 11 tests in a spatial logic for the numbers 1 through 9? This is a state value that the spatial logic tests for to determine if the number is in the range 1 through 9. Spatial software must leave a trail of breadcrumbs. This is pure overhead. It must track down where it was. It's got to go back through those breadcrumbs. This is pure overhead. It's difficult to maintain, excuse me, because when you come back into a spatial software application, you must understand the overhead. And keeping the overhead straight is just as important as understanding what the application is trying to do work-wise. Which also means it's going to be difficult to modify, because again, you've got to keep that overhead straight. Temporal software keeps the temporal pointer, reduces complexity, eliminates much of the overhead, it's easier to maintain, it's easier to modify, add a new rule, change the logic. Software quality. It's my contention that testing doesn't improve quality. Testing fixes some quality problems, but ultimately the quality is still poor. Temporal engineering improves quality, reduces overhead logic, fewer things can go wrong. Where I've used temporal, I've used it doing some disk driver analysis. I've used it on a couple of very large data migration projects. I've used it for data filtering, in Lecture Parser Data Analyzer for cleaning up data. I've used it with a radar control system. I'm currently doing a robotic arm control using temporal logic. I've used it in some embedded applications and in Code Generator. And that's the end. I want to thank Bacadero Technology for inviting me to speak at this presentation. I'm now available, assuming my voice will hold up, for questions.